Hello again and welcome to part 3 where we're looking at the UNI-T UT61E+. Again, this meter was damaged, but I've since repaired it. We're going to start by looking at the contrast of a few different meters. I have all the meters basically set at the same angle. On the left we have the Summit. This is sold by TPI. It's the 194.2. Of course, the Fluke 189. Here we have the Bryman BM789. Here's our UNI-T UT61E+. Of course, the Bryman BM869S. Here's the Yokogawa TY720. And of course, the UNI-T UT181A. This is looking at all the meters head on. It's tough to beat this UT181A for the display. Let's go ahead and enable the backlight on all these. Again, the TPI Summit, the Fluke 189, the BM789, the UNI-T UT61E+, Bryman BM869S, the Yokogawa TY720, and again the UNI-T UT181A. Okay, I've gone ahead and brought all the meters outside. You can see I've added Dave's 121 GW. So the sun's not really bright today, but should give you some idea. We'll just try to look at them face on. And this is from above. Try it from below. I'd say they're all usable out in the sunlight. Just looking at all the meters from about 2 feet away. I'd say that they're all usable in the outdoor light. If I had to rank them, I'd say this Yokogawa has the worst contrast. So I've moved all of our meters to try to get them in the direct sunlight. It's very difficult for me to read that 181. The 121 GW is a little more difficult. And you can see it doesn't really matter the angle. The contrast for that UNI-T is just a lot better. You can see the same thing for this BM789. Fluke isn't too bad. Again, here's the TPI, the 869S. And of course the Yokogawa. You can see we're back out in the motorcycle trailer. It's a couple of my bikes. So what we're going to be doing is again exposing this UT61E+ to a couple of different chemicals. We're going to start using a little methanol, and again this methanol has a top end oiler. This is the oiler that we're using. Basically what we're looking for is if this attacks any of the lettering. Put it right across the lens as well. Doesn't look like there's any problems at all. Next we'll be using some VP fuel. This is a C16. Looks good. I'm not seeing any signs where that's had any effect. Looks good. Currently all 4 meters are attached to my RF generator. I'm currently applying a 60 Hertz 1 volt sine wave. What I'm going to be doing is increasing the frequency. That'll give us an idea what the UT61E Plus's roll-off looks like compared to the other 3 meters. Let's start by reducing the frequency. You can see we're currently at 5 Hertz. Notice that all 3 meters have started to roll off. The UT61E Plus is definitely the highest of the 4. Let's go ahead and we'll start increasing the frequency. Currently we're at 312 kilohertz it looks like. You see 313 or so kilohertz. Let's just verify that with the BM789. Let's have a look at that with our UNI-T meter as well. It's odd. Should be able to read this. Let's try it in the Hertz mode. There you go, so 313. And of course with the Fluke, see all 4 meters are basically reading the same. So this is definitely the 3 dB point for the Fluke. You'll notice how the BM789 is peaking up quite a bit. Looks like the BM869S as well as the UT61E Plus are by far the closest of the 4 meters shown. Let's go ahead and we'll take the frequency up a little higher. This is currently 480 kilohertz. And we can see this is our 3 dB point for the BM869S. And you can see the UT61E Plus is also starting to roll off. Here you can see we're up at 584 kilohertz. And we are now just at the 3 dB point for the UT61E Plus. Alright, so off to my left you can see I have one of my high voltage power supplies out. It's currently attached to all 4 of these meters. All 4 meters are set to their DC voltage modes. You can see we're at 29. Both indicators are off. Right there, so 32 volts. You can see all 4 meters are basically reading the same. Looks like our UNI-T is a little low. This is the top end of my power supply, so almost 1,000 volts. You can again see all 4 meters are reading roughly the same value. I've changed our power supply to put out a symmetrical waveform. Of course we'll be able to change the bias voltage with this. Again, this will be 60 Hertz and a 50% duty cycle. I've changed both meters to their DC volt mode. Let's go ahead and turn on our power supply. And you can see the UT61E is already hunting. If we go to AC plus DC, you can see we're outputting about 275 volts. Again, if we're in the AC volt mode, you can see 275, and again our DC voltage is essentially 0, or basically 5 volts. Oh, there, it just caught itself. So it looks like it's reading about 13.6. just for the fun of it, let me turn off the power supply and we'll attach our fluke meter. We're going to set this to the AC plus DC volt mode, and again we'll turn on our power supply and you can see it's reading roughly a -2 volts DC. Let's just go ahead and we'll select the manual range, and you can see like 11.5 volts. It's off by quite a bit compared to 1.8. And again, what's our Bryman meter reading? Yeah, like 1.6. So yeah, I'm saying that this reading's off by a fair amount. Again, I'm not too surprised that this UT61E is having a problem with this. Now let's just change our meter back to auto range, and let's go ahead and increase our voltage. Oh, it's having trouble again. You can see we're up at 21 volts, 22 volts. Looks like it caught it, so let's go ahead and continue up. Looks like the auto range is just having a problem with the lower voltages. It seems to work fine as soon as we get above about 20 volts. Let's just try going negative with it. Here again, you can see we're down at about 6 volts and the meter's hunting. Here we are at a -8. It's still hunting. Again, if we go to manual range, there you go, so 8.2 or so volts. Let's see where it picks it up at. So there's 13, 19 volts right there, so 21 volts again. About a -530 volts. Again, that's DC. If we switch it over to AC mode, see about 523 volts. And again, this shouldn't be affected by changing our DC bias. And you can see it's not. So it looks like the UT61E Plus has some problems with these biased waveforms. Again, that's a very typical problem, and one of the things I noticed with the new BM780 series from Bryman. That's probably the main thing that we focused on when we were going through the initial reviews of this meter. And again, they've done a very good job correcting those initial problems. For this next test, we'll be using our transient generator. Again, this generator can output a 220 volt AC waveform that's gone through a full wave rectifier. So I've just got this test light bulb. This is a 120 volt rated for, I think, 40 watts or something. Now this transient generator is monitoring the current. So this is currently drawing, looks like about 300 milliamps. I can program where this thing cuts off at. So if the meter is drawing too much current, then the generator will automatically turn off the output. So we're going to be applying this full wave rectified waveform to the front end of our UT61E Plus, and then we're going to rotate this through all the different modes. So let's go ahead and turn it on, and you can see we're getting roughly 120 volts RMS. Let's go to the DC mode, and you can see 233 volts. Here we're in the millivolt range. Of course, it overloads. Here we're in the resistance mode, and of course the PTCs now are going to be enabled along with that low voltage clamp. Here we're in the frequency mode, and again, because it is full wave rectified, we're seeing 120 Hertz instead of 60. I don't think the HFE is going to do anything, but we'll select that. Showing a beta of 61. And that's it. Now we'll go ahead and functional test the meter. Alright, so our UT61E survived that test just fine. So what we'd like to do next is go over to our grill starter test. Again, this is going to output, I think it's roughly a 5 amp peak. Again, I had characterized this grill starter in a previous video, and I'll go ahead and link that in the description if you're interested in seeing what that waveform looks like. But again, it's nowhere near what the IEC standard calls for. So previously, I had modified this UT61E. You can see this has a lot of modifications to it. Here's our little chopper amplifier. This meter can actually measure 20 amps. This is my homemade shunt. You can see where I've machined up these brass inserts and then silver soldered it. onto the shunt. You can see this area of the circuit board was beefed up. Again, that's to handle the 20 amps. This has a larger style PTC, and it also has the MOVs installed. And this meter also had some of the worst temperature drift of all the meters that I've looked at. Down here you can see my small temperature compensation circuit. I've also changed out the original potentiometer. Of course, this meter also has that adaptive backlight. So again, this meter would have originally failed with this grill starter. And the reason that it failed is because they had a high impedance input path for DC that fed right into the main control IC, but they also had all these frequency compensation networks, and that input tied straight to the input jack. So it's not behind the PTCs, it's going right to the front end of this. So there's no additional clamping. And what ends up happening, of course, the transient coming off of this, it's very fast. We're talking 5 amps in sub 1 nanosecond. And that transient would blow right through that high frequency compensation and right to the IC chip, and of course that would damage it. So what I had done is I had limited that current, and I did that by adding 2 small resistors, which you can see right there. And that essentially limits the current going to the IC chip. And this meter had survived this grill starter all day now. But it's hard to say with this meter how that's actually done without actually reverse engineering it and having a look at it. I'd like to point out too that this meter right now is looking at our 10 mega ohm resistor. You can see it's reading spot on. So no damage to this meter at all right now. But I would like to point out again that I did damage the meter in the very first test. When we rebuilt it, I had used a different transistor than what this meter was originally shipped with, and those are the transistors that I had used in this BM869S to improve its robustness. Alright, so just to be clear, if this meter actually survives this grill starter, that doesn't mean that if you go out and purchase one of these brand new, that it would also survive it. Likewise, it doesn't mean that if it fails this test, that if you bought a new one, that it would also fail. We really don't know. Again, the meter's been modified, and that's why we're not going to be collecting any of this data. So again, we'll be applying 5 transients, both positive and negative, with the meter set to each mode. So here we go. Woo. I don't have a good feeling about this. Still open circuited. Let's try HFE. And let's reverse the polarity. Let's just have a quick look at this. We'll start off with the AC volt mode. Again, this should be roughly 70 volts. See, 65, that looks about right. This should be roughly 2.5 volts. That looks good. Let's go to DC volts. This should be 5 volts. Looks good. And this should be roughly 60 volts. Looks good. Let's try it in the millivolts. For AC, this should be about 118. Looks good. And let's just try it in DC. So this should be roughly 20 millivolts. Looks good. Let's just try frequency real quick. Again, this should be 60 hertz. And this should be 60 hertz as well. Should be 30 and 120. Let's try it in the AC volt mode as well. So again, this should be 120 hertz. This should be 15. So that looks fine. Let's just go to frequency, and again, this should be 15 and 120. Looks good. Alright, so let's try resistance. This will be our 10 mega ohm resistor. Again, it takes the meter a while to settle. Looks good. Here's our 1 mega ohm. Really good. 100K, good. 10. Yep, 10K is good. Here's 1K. Looks good. 100 ohms. Looks good. Here's our 50. Looks good. And here's our 1 ohm. Looks good. Let's just try it with a higher value. This is our 100 mega ohm. And it's going to take it a little while to settle. Good enough. Let's go to continuity mode. Looks good. And let's try diode check. Again, this is an open. Here's our short. This is a single silicon diode. Looks good. Here's 2 in series. Looks good. Let's try capacitance mode. This will be 150 picofarads. Spot on. This will be a 1 nanofarad. Spot on. This will be a 0.1 microfarad. Looks real good. And this will be 1 microfarad. Really good. 10 microfarads. Good. And 100 microfarad. Looks really good. We can check the current input, but again, I'm not doing anything that should damage that. But this again is going to be a 100 microamps, 10 microamps, 1 microamp, and 100 nanoamps. So a little bit of a surprise. It looks like our UT61E Plus has survived the grill starter. Again, could be a result of changing out those transistors, or it could be that they've changed the design of the meter to be able to handle that. Either way, it's impressive. Alright, again, this is our homemade ESD gun. The waveform coming off of this fairly closely matches what the IEC standards call for. Again, the ESD is called out in the EMC standard, not the safety standard. So again, we'll be applying 5 transients, both positive and negative. And here we go. And again, we'll flip the leads to run the negative transient. And that's it. I'll go ahead and functional test the meter. The UT61E Plus survived that test just fine, so that is all the ESD testing we would normally perform. So this next test is going to be a little bit different than what we had previously ran with our transient generator. Again, with this transient generator puts out a full wave rectified AC waveform. This viewer had asked that we basically attach the meter to the line, and we do that with the meter set to the ohms mode. So I currently have these 2 meters set in parallel. You can see I'm putting out roughly 53 volts. I'm going to set this to the resistance mode. And you can see there's a little bit of a draw. Now what I'm going to do is turn this thing up, and let's see if we can damage this meter. It's a fair bit higher than what they had asked for. You can see we're all the way up to 340 volts. I'll just turn off that power supply. I would imagine the PTCs are going to be quite hot. But you can see it's definitely reading an open circuit. And here we are with a short. No problem. Let's just try it with our 10 mega ohm resistor. Again, takes a little bit to settle, but it looks like no harm done. This will be our 1 mega ohm. And here's our 100K, our 10K, our 1K, our 100 ohm, our 50, and our 1 ohm. And again, this would be the 100 mega ohm. And let's just try it in continuity. Seems to be fine. And again, this is diode check. Here's our short. Here's a single silicon diode. And here's 2 in series. And let's go to capacitance. Here's our 150 picofarads. And here's the 1 nanofarad. Here's our 0.1 microfarad. So yeah, no problems, at least with this particular meter. But again, this meter has been modified. And again, to be clear, those transistors that are replaced, those are part of the low voltage clamp, and those do come into play when we're in the resistance mode like that. So again, would a brand new meter stock off the shelf survive this? I don't know, but I can tell you that this particular meter does. I'm pretty confident that a stock one would, but the only way to know for sure would be to go ahead and test it. Well, I don't think I'm going to press my luck with the UT61E. Looks like we're already at about a half an hour, so I think we're going to end this video on a good note for a change. So my plan for part 4 is to go ahead and start transient testing the meter using the smaller generator. I haven't decided yet if I want to temperature cycle the meter to get an idea on the drift. And again, the other thing I'm thinking about doing with this meter is to life cycle the switch. I've never done that with the UNI-T meter, and I think this is probably as good a meter as any to try it with. So that's all for now. I hope you enjoyed the video. Later.